Hi, folks. We don't have a lot of time here. It's a half-hour talk, so I'm going to get started right away. My name is Devin Horsman. I'm from Twisted Oak Studios in Halifax, Nova Scotia. I'm going to talk to you about extended coroutines so that you can do some more useful things with them. So we'll start with me letting you know that this is going to be an intermediate to advanced scripting talk. It's going to be focused on C#. So Unity script users, you may find that things don't look exactly like what you're used to. That's because there's a lot of sort of syntactic sugar that goes into coroutines in Unity for Unity script users. We're going to talk about the concept of executing tasks over time and how that's commonly handled, and then we're going to introduce coroutines. We're going to talk about how yield and IEnumerator work, and those are the sort of things that coroutines are built off of in Unity. Then we're going to talk about how coroutines are implemented in the Unity engine, and then we're going to extend coroutines to add some useful features to them. So, as we are all aware, you work with the concept of frames in game engines all the time. For instance, in Unity, the update function for each mono behavior that you create is called once per frame. But we often want to do things that take more than one frame. And the kind of natural way of thinking about it would be to continue to program things imperatively, like to say, add a little bit of alpha to this object to make it transparent, and then you do that 100 times, and then it's fine. But if you do that, you're going to block execution if you use, like, for instance, thread.wait. So we need to figure out how we're going to execute things that take more than one frame's worth of time in Unity. We also want to know when that thing is finished so that we can go off and do something else. There's lots of tasks that follow this sort of pattern. That's cutscenes and animations. So for instance, you may want a camera to move and then to start another camera and have that move. You may want to start the dialogue and only display the next piece of dialogue when the first one is clicked through, and those sorts of things. You can think of AI sequences. For instance, an enemy in a game may want to locate the player, then chase the player if he sees him to shoot him. These are the kinds of things that you might want to program that take place over more than one frame. And then there's also expensive operations, things like computing a path with a path in pathfinding, or some other thing that's quite expensive, like processing the AI. So the big idea here is that you've got your main logic for your game, and then you've got these little tasks that sort of spin off of that main logic. And we think about those as running in parallel. But I just want to have a little aside here and kind of maybe clear up a common misconception that people have about both coroutines and many things in Unity. And that's that everything in Unity is not solved with a sort of threading approach, what you see here on the left side of the screen, where a task waits for another task to finish it, and they're both executing at once. That's sort of the logical way of thinking about it. But in reality, it's all time shared. That is, little slices of each task get to go one at a time, and you cycle through each of the tasks very quickly, and that's sort of how you get the illusion of multiple things running at once, right? It's not like all your update calls are executed in parallel. They're all executed sort of one at a time. They each get a go, and then your frame's over, and you start again. Likewise, that's how coroutines work in Unity. So that's just a quick aside to clear up a common misconception. So let's look at a common kind of task you might want to do. This is sort of what an AI might do in a game. He might want to like find the last known location of the player character, look for the player, and then when he sees them, fire at the player until the player's out of sight or he's out of ammo, and then he might either want to move to the last known location again or reload. This is an example of what's called a state machine. State machines are the classic way of doing execution over multiple frames or over time in programs. They have some drawbacks, though, and I'll just bring up a state machine here. So this is just the kind of cruft code that you'd find in basically every sort of state machine you'd see. Up at the top there, we have a list of the different states that the state machine can be in. Then we have a variable for the current state. I have a little comment in there that says that all the local state variables for the states go here, and I'll talk about that in a second. But if you look at the update, you see that it's this switch statement, and the switch statement is basically saying each update call, find out which state we're in right now, and process a little bit of that. And then, so that's the basic idea of how the state machine works, and then that would jump to each of the state's functions. But in order to sort of remember anything that was going on last time the state machine was called, it's got to store all of its local state variables. Each state needs to store its state variables in the class itself. And that can lead to, obviously, giving people access to variables that don't need them, or parts of your code getting access to variables that shouldn't get them. It can lead to many other things, like a greater kind of cyclomatic complexity. That's the number of different ways a piece of code can branch, and that's directly tied to the number of bugs in a program. There's a lot of code dedicated to accounting, so the more code that's in a particular module, the more likely there is to be mistakes, so you're more likely to create bugs. And then the other thing that's there is that it's sort of half declarative and half imperative style of programming, in that you write this thing out sort of like the state machine drawing by, listing all the states and then jumping to the appropriate states. But you're trying to write imperative code that happens in a distinct order, and the lexical order of the code isn't very closely tied to the order that it operates in. And that's another way that people get confused and make bugs. So what does that same code look like sort of as a coroutine? And this is kind of what blew my mind about coroutines the first time I saw them. All that code there that we saw before had absolutely no logic in it at all. It was just the kind of scaffolding in order to be able to make the most basic of state machines. This is actually has the entire kind of top-level logic written out in it, and it's about a third as long. You can see there that the start function, which we're going to call a coroutine, start is a coroutine here. It says while true, so forever basically. Move to the last known player location, look around until you see the player. Well, you can see the player and your clip's not empty, you're going to shoot at him. And then one of those two checks will be false eventually. And then you say, if the clip is empty, reload, and then you start the loop again. And that's basically the whole idea for the logic there. And then for each one of the kind of subparts of that, you'd have a function, and you kind of get to compose your program like you're used to composing it. Things get too big, and you kind of pull it out into a separate function. And coroutines make it possible, of course, now to write your entire sort of state machine in an imperative style. And that leads to fewer bugs, shorter lexical code, and general happiness from developers. So what are coroutines? Well, they're not magic. Sort of the first thing you think of when you see them, especially if you started with Unity script, is like, how can this work? I'm not used to this. Maybe you started with Java programming or JavaScript programming, and you've never seen the kind of code that could possibly make coroutines work. It feels very magical. It feels like Unity is taking your code and turning it into something else that you're not seeing. And yeah, it's not magical. It all makes sense if you figure out what each of the nitty-gritty details are, and we'll go through those right now. So the first thing that's special about them is that they use the IEnumerator class type and yield keyword. which are probably new to a lot of people before using Unity. So let's take a quick look at what those things are. So IEnumerator is essentially, it's a type that represents an iterator. It exposes three methods. One's called moveNext, which kind of advances the iterator to the next item in the list. And if you're not familiar with the concept of iterators, it's basically a way of asking for sort of a sequence of objects. So the moveNext outputs the next value in the iterator. Current gets that value, and moveNext will return false when it's all out of objects. So that's basically what an IEnumerator is. But this yield keyword, when it's detected by the C# compiler and shows up in a function that returns the type IEnumerator, will transform a function into a state machine that implements the iterator that this sort of code describes. So basically, you can think of yield as a sort of return that leaves execution in the same place until you come back and restores the local stack of the function. That is, all the variables that were local to that function will be the same as they were the last time you were in that function in your execution. So this IEnumerator, or this function here is implementing the Fibonacci sequence. So if we go through it, we can see that we start the first number, f of k minus 1 as 1, and f of k minus 2 as 1. And then we return to ones here, which are the first two values of the Fibonacci sequence. And then until we're out of ints that we can go through, we add the two together, swap each one back one, and then return the next Fibonacci number. And this is how we might use it in our code below there. We'd say, okay, calling that function returns an IEnumerator, which is basically a pointer to the start of the function. And then we generate the first 10 Fibonacci numbers by calling moveNext 10 times. And if something went wrong, then it would break. Otherwise, print out the next number. And yeah, it's pretty straightforward there. So the idea of coroutines in Unity is really to just use the yield keyword in IEnumerator, but instead of you needing to call moveNext to advance it, it's going to call moveNext for you at intelligent times. For instance, when some piece of execution that happens in the background is finished, or when some number of seconds have elapsed, or when some other coroutine is finished. So Unity is using the return value that you gave last time you entered the function as its indicator of when to call moveNext the next time and start the function back up. So what are the different things that you can return that Unity understands? Well, there are these objects that inherit from yield instruction, and they have special meaning to Unity. The ones you're probably familiar with are, like, for instance, www class, which says, hey, don't call this function again, or don't call moveNext again until we're done downloading the data that I asked for. Wait for seconds, which says don't call moveNext again until this number of seconds have elapsed. Waiting for the end of frame, which says when everything is done for the frame, including rendering, just call this for me. And the coroutine, which is probably the thing that makes the whole thing so useful, is wait until this other coroutine is done before resuming execution of the one we're currently in. And then for any other types, Unity will wait for one frame and call moveNext after all the update functions have gone for all the other objects in your game. So I hope that explains basically what coroutines are, how they work. But there's some routine problems with coroutines. The first one is they don't have any return values. So if you want to use a coroutine to do a bunch of work for you and you want some result of that work, so for instance, finding a path using whatever pathfinding system you're using in your game, or say waiting until the user gives you some input and then returning it, which is another common task. The way that that coroutines are set up, there's no way to get a value out of a coroutine if you yield to it. So, in this case, if we wanted to get a reference to the player by saying look around until you see the player, there's nowhere for that value to go unless we make some static variable somewhere and put that reference in at the end of the coroutine we're calling. The next big problem is that they have no error handling. So if you run into an exception anywhere inside a coroutine, it just gets spit out to your console, and you have no way of handling that. So if you were to publish a library that had some coroutines in it, and it took some user input, there's no way for the person using your library to handle the exceptional cases. It just basically has to say, okay, the coroutine failed. The only way you can really deal with it is by, say, setting a bool if the coroutine was successful or not in a static location, and that's obviously something you don't want to do. It's really good to be able to use exception handling to deal with error cases or even unexpected cases that come up in your coroutine, and it makes your code more composable. They also have really terrible canceling semantics, and what I mean by that is that there's no nice way to cancel an individual coroutine in Unity. You can cancel all the coroutines that are running on a single object, and you can cancel a coroutine by name that's running on an object. But in order to use that, the cancel by name feature, you need to start it with a string argument instead of starting it with the actual function call that returns the IEnumerator. And what that means is that now you've got this stringly typed code that would only get an error in it would only be caught at runtime instead of at compile time, and that's something that no developer wants. That's sort of a really obvious flaw. And there's another downside to that, which is that if you're starting a coroutine with a string argument, you can only start coroutines that are part of the script that's on the object that you're calling the start coroutine on. And you can't call a coroutine onto an object that's, say, a static function. And that's never very good either. It means that it's harder to create libraries and harder to compose things in your code. So we could make our own coroutine system. We now know how Unity's works, and we could take advantage of that knowledge and write a coroutine system from scratch, one that stored all the currently running coroutines. We could call it with a different name, store the running coroutines in lists, and then look them up at certain times in your game and call the ones that are ready to be called again. But that's possible, but it's really intrusive in that if Unity adds some new feature that has a yield instruction, now you've got to update this system. Additionally, if you won't be able to use some of the built-in stuff, like you can't use the standard sort of yield instructions, right, without rewriting them. But what if we had one weird little trick? You could kind of stumble across something like that. So let's talk about what that might be. The idea for the weird little trick is to actually sit in between every coroutine that runs and Unity's own start coroutine, and then pump, like when Unity tells our internal, the thing that's sitting in between to run, we look at that and we pull out the next thing from the original coroutine and we decide what we're going to do then. So we're basically sitting in between each of the emitted values from the original coroutine, and that's where we can go in and extend things and change things and decide to cancel things. And let's see what that looks like. So first thing we'll talk about is adding return values, and we'll kind of walk through the process of this. So here's what I mean by having this sort of internal routine. Is the text big enough? I'm just gonna, sorry. It could get bigger, okay. That's good? Okay. So this function is called internal routine, let's call it that. It takes the original coroutine that you intended to call and calls move next on it until the coroutine is over, and then breaks if it is. After each move next, it checks what object the internal coroutine yielded. It can print out then what that object is, and then return that value to Unity, because this is the thing that we're now passing into Unity's start coroutine. So if we look down at the bottom there, you can see we're calling start coroutine with our internal routine, which is taking the original routine we wanted, and then sort of sitting in the middle there. And that'll let us see each of the values as they come out of the original routine. So let's see how we might implement returning a value from that. So what we could do is check each of those values. So I just added a little bit in the middle here, and I said if the object that was yielded isn't null, let's get the type of it. And we'll see if it's the type that we care about, whatever type that is. And if it is, we'll store it in some variable somewhere, and we'll end our internal routine, which will in turn end the coroutine in Unity. Otherwise, we yield the value and keep going. So this is all kind of ugly. We've now made a static variable, and now you've got to stick this internal routine thing in front of every coroutine you make, and that's pretty gross. So we need to start making it pretty. So we'll start by making an object that sort of wraps this thing. That's sort of just, Unity has its own object called a coroutine that's a yield instruction. Well, let's make coroutine T, which is a coroutine that takes a type argument, and the type is the type that you're waiting to see from the internal routine before you end. And it's also got this public coroutine without a T, which is the type that Unity usually yield to in a standard. That's what start coroutine returns, sort of what I mean to say. And it's got its own private variable called return val. And then everything else looks the same. Then we have this nice little thing up here at the top, and it's a static class with a thing called an extension method, which is another feature of C#. And I don't know if anyone here has seen extension methods before. Could I see a raise of hands for extension method knower-abouters? Okay. So it looks like about half of you. Well, for those that don't know, and for the people watching from the internet, an extension method is a way of kind of injecting a new public method into an existing class. So if we look at this syntax, this name, monobehavior ext, doesn't matter. It could be anything. But what matters here is that we've got this function defined. It's public. It's static. It returns a coroutine T. It's called start coroutine T, and the first little argument to it has a this in front of it. And basically that's saying what's on the left-hand side of the thing that we dot, that this method is called on. So if you say, like, some object that's a mono behavior dot start coroutine T, this function will be searched for and found and called. And then the first argument to it would be the original coroutine. Is that sort of clear to everybody? Great. And then inside there, we make a new coroutine T object. We call start coroutine like you would have in your original code, and we have the internal routine of that coroutine object that we just made, which is the same internal routine thing that we've been talking about this whole time. And we pass in the original coroutine, and then we store the result of start coroutine into the coroutine object that we just made so that it can be yielded to, and then we return the object. And it would be used like this. So you just call start coroutine of type int with any IEnumerator function. The IEnumerator function looks just like any other coroutine you've ever written, except at the end it returns a 1. So what would happen in this case is run for 2 seconds and then return 10, sorry. And then we store the output of start coroutine and we yield to it, and that's the same as yielding to a start coroutine normally in Unity. And then we can log the return value, which is a public value in the coroutine T type. So let's move on. We've only got a little bit of time left. So how do we add error handling? Well, we want to see if an exception occurs and then catch it. We're going to store it into the coroutine type. And then we would also store the stack frame the coroutine was started from. When the user tries to access the return value, if there was an exception during the execution of the coroutine, we throw that exception. So let's look at that. So we've added value is now a property instead of a member. In that, we check if there was an exception, and if there was, we throw that. Otherwise, we return the return value. And then in our internal routine, we add a try block around move next. We catch any exception, and if we catch it, we store it in that E variable, and then we end the internal routine. And then that would be used like this. So we can start our routine that we know throws an exception. We can yield for it to finish, and then we try to access the value, but we find that there is an exception and do something about it. And finally, let's add better canceling. So right now, we have this new coroutine T object, and we can call functions on it. So let's let the user call cancel on it, and if they call cancel on it, then we'll have it throw an exception and store it, a canceled exception internally. When some other piece of code tries to access the value, then they will get a canceled exception. So let's see what that looks like. We just add an is canceled to the top of each while loop. If it's canceled, we, let's fix this here. If it's canceled, we make a new coroutine canceled exception and store it in the exception value, and then we break from the internal routine, and then it would look like this in use. So let's say that we started the routine we're going to cancel, and we, instead of yielding to it, we wait for 1.5 seconds and then call cancel on the routine. Sometime later, we try to get the routine's value, and we'll find that there's a canceled exception, and we can catch that and deal with that separately from other errors. That's everything for my talk. You can email me, you can text me, we can tell jokes to each other. You can find me on Twitter. You can go see the Twisted Oak Studios blog that has many other things like this. And you can find the code that we just talked about on GitHub under Twisted Oak Unity Utilities on our GitHub. I'll be around after Jonathan's talk to answer any questions that you have. Thanks.